So let's get started reviewing this Pedigree Practice AP Biology worksheet. This is from the AP Corner, so let's get started. So looking to the right, I see a pattern. I see a pedigree pattern, and we should recognize clearly that the squares are males and circles are females, and the circled, or the shaded, I should say, shapes are the individuals that are inflicted with the disorder. This, of course, is the first generation, the second generation, and the third generation. So looking at this pattern, and generally speaking, it's one of four patterns. There's autosomal dominant, and which means we're going to have autosomal, of course, is non-sex chromosomes, and autosomal recessive. And then we have the X-linked dominant, which means now we're talking about an X-linked gene. Okay, and then of course an X-linked recessive. Anyway, getting back to this, looking at this pattern, I can see that there is a generation 1, missing the disorder. And that kind of tells a tale that this might be autosomal recessive. It doesn't prove it 100%. There's certainly going to be inheritance patterns that do miss or do skip generations, but this one seems one that is the most picked on in the AP curriculum, and one you should be able to identify real quickly. So looking at that, I see that the first generation doesn't have the disorder and that the children do. I know I can eliminate autosomal dominant usually, but getting after this, how do I explain that the parents, let's say in the first generation right here, don't have the infliction? Well, for me, it's very simple. Both of these could be carriers, right? So this could be a little a, and this could be a little a. And if you were to do a Punnett square, and that's really helpful here if you don't see that, you can see that clearly we can have little a and little a here, okay? And I'll make this bigger, up close and personal here. And if we don't have the infliction, we could be either, well, homozygous dominant, or we could be, well, in this case, we could be a carrier also. And again, if you don't see that pattern, let's write that. Because in this, in this cross, and I made a mistake, as I often do sometimes. So in this cross, and it's good, again, good practice, I can get that homozygous dominant, or I can get that heterozygote, which we call a carrier, or another carrier here, or the homozygous recessive. As you probably have learned somewhere, here's your 3-to-1 ratio when you do that with heterozygotes. But we're going to call something with a little a carrier, because you have one chromosome that has a mutation that doesn't make the right protein for whatever disease this might be, or whatever process the human needs or organism needs. So in any case, we're not sure here yet what this is, but if I look carefully, here we are skipping another generation. If this is going to be an autosomal, which means non-sex linked cells, recessive disorder. Recessive means in order to have the disorder, you have to have both chromosomes or alleles recessive. That should make sense. Both chromosomes have a gene that is mutated that doesn't make the right protein. That leads to the allele. So in any case, I'm looking at these individuals here. Well, they were going to be a little a little a. And so can we explain this? Well, the only way for little a between these two individuals here is in second generation is that this box here of this male here in the second generation must be a carrier. Has to be a carrier, because one of the two chromosomes has to be given to the offspring. Right, you get one from your mom, one from your dad. So in any case, this one also must be a carrier. And this individual, we're not sure because we don't see its children, but we know it's not little a, little a. So I'm clearly seeing a pattern here. I can explain this. Let's see if I can keep going. If I'm skipping a generation here, how can two parents make a offspring that's infected? Again, they must also be carriers. That's the only way to explain it. And you say, well, isn't there another possibility? Couldn't I be little a, and do that? Sure, but then if I'm little a, one of these boxes or these circles or these individuals, males and females, would be inflicted, right? Because that'd be the case. But if this is the pattern, okay, and you're a carrier, two carriers, at least two carriers have to come together to make an offspring. But again, it's not circled in. So again, another understanding that how did we make carriers in the second generation right here? The only way to explain that is that the parents here are little a, possibly, or a little a, or carriers. Okay, now in this case, we probably could say that one of these two individuals could also be big A, or, okay, because if you do that Punnett square, okay, and put a big A there, okay, let's do it down here. So big A, little a, okay, if you do that cross, okay, we still can get some what? You still can get some carriers. So not 100% sure, okay, with these two boxes here, okay. So these two boxes could be, one of the two must be big A or little a, or the other one a little a. So this is definitely not certain that they're both carriers, but it still works, okay. So in any case, so what led me to look at this was, again, skipping the generations, although that's not 100% always the answer or the way to identify 100% autosomal recessive. It certainly is helpful to get the ball rolling here. So in any case, this is another question mark, okay? And you could figure out what that could be. If it's a homozygous recessive cross, well, this one could be big A, or it could be a dominant, or I should say heterozygote. Okay, same thing here, and we don't know which one it is until they have children. All right, so basically I was able to go backwards and forwards here to support my thinking that if I have parents who don't show the disorder, but the offspring do, then clearly this is a pattern that supports that. So I'm 100% certain that this answer here, okay, is autosomal recessive. So that is the answer here. Now the 2 says provide at least one piece of evidence for your claim, and many ways to say this, but you could say that parents that have children that are inflicted, they themselves will not have the disease. So again, you could talk about how that works there. So again, many things you could say here, but I would go that, again, you've got parents who must be heterozygotes of carriers and don't have the infliction, but their offspring do is the best way to explain that. Okay, and again, this anywhere you can write a Punnett square to support that, okay, definitely helps there. And again, that supports the idea that you can have this skipping of the generations. All right. Any case, on to the second one. All right, so this pattern to the right here in the second question, I see, like I saw with the first one, is skipping of the generation. So this is generation 1, 2, and 3. So more, I'm kind of leaning toward another scenario where I could have a autosomal recessive disorder. And so let's see if I can support that. I see in the second generation, I see children from the first generation that have the disorder. And if that's the case, then I would put little a. Now, I'm not sure if this can be supported. Let's go see. The parents don't have the infliction, so they must at least, okay, well, they have to be carriers. They both have to deliver, okay, at least one mutated allele or recessive allele. So it makes sense that they must be a, and heterozygotes are carriers. It must 100% make sense because they both have to deliver one recessive allele for this to happen. Because if we have what? If we have children who have the infliction, one chromosome or allele comes from each parent. So these must be homozygous recessive. There's no doubt about it. If this is the inheritance pattern, and this is the inheritance pattern, because I can see clearly that if I was to do a Punnett square of these two heterozygotes, I know that I'm going to make homozygous recessive individuals who have the disease, but I'm also going to make carriers. And you say, why am I putting a carrier here? Well, I can see that in the third generation, we have a individual, a female, who has the disease. So again, homozygous recessive. And in order to deliver two homozygous or two recessive alleles, then this individual here must also be a carrier. How do I know it's a carrier? Well, it's not showing the disease, right? And it has to have a recessive allele for each parent in order to deliver a child with two homozygous recessive alleles. And of course, if you do a heterozygous type of Punnett square, there's other possibilities here. Okay, this individual could be big A, okay, because you can both deliver the A's here. It can't be homozygous recessive because it would be grayed out, but it can be a heterozygote. Those are the possibilities. So this one could be both. So this is definitely showing us an autosomal recessive pattern again. All right, and then question is, what could how can this individual be here? Okay, which I'm going to call number 1. Well, that one, let's think about this for a second. It could be a couple of different things, okay? And what I do know is that 3 must be a carrier, or I should say the individual, the male that's born here must be a carrier. You say, well, how do I know that? Well, it's going to get at least 1 recessive allele. And because it's not darkened in, it doesn't have a second one, this has to be a dominant allele. Okay, so when you think about what this individual here has to be, well, it can't be homozygous recessive. It would be shaded in. So it's either going to be AA, or homozygous dominant, or a carrier. Those are the 2 possibilities. Okay, and if you do the Punnett squares, you can see that both of those scenarios will produce a carrier or heterozygote. Okay, so that's really important. So we go back to the question. Okay, this inheritance pattern is absolutely autosomal recessive again. Okay, autosomal just means, again, we're talking about a non-X-linked, non-sex-linked genes here. So recessive just means for the individuals they have to have 2 recessive alleles, 2 broken genes. 4 says, highlight one individual whose genotype is unknown. What additional information would you need to determine her genotype, or his or her genotype? Okay, well, the ones that are unknown is the one that I labeled 1, and I'll name this one 2. Okay, I'll just call that 2. So in 1, okay, I would need for them to have more children. Okay, so for 1, if they had more children, and let's just pretend that it had a female, and if we shaded it in, whoa, that means it has the what? It has the little a. And how would that happen? Because you only get one from this parent. That would mean that you'd have to get another one from this parent. So that would eliminate the homozygous dominant. So in order to figure out what the genotype of this individual here, we would need more children. And of course, we need more children, and to definitely know, we need to have children that actually are inflicted. In number 2, we'd have to have children as well. Okay, so that's where that's coming from. On to the third pedigree. So looking at this third pedigree, the one thing that jumps out to me is that there is individuals with the disease or disorder in every generation. So this could be non-autosomal recessive. Okay, so let's talk about this. So if I look at the pedigree up close, I can clearly see that the grandfather and grandmother of these generations, first, second, and third, both have the disease. Okay, now, if this was an autosomal recessive disease, these guys would both, the grandfather and grandmother would both be homozygous recessive. And because there is no dominant alleles, every single what? Offspring from that family would have to be colored in. And that's not the case. So that's a good way to see that this is not autosomal recessive. Okay? So this looks to be possibly, now if it's not autosomal recessive, what do I got left? I've got autosomal dominant, and I've got these X-linked type of disorders or inheritance patterns that these disorders have. Well, if it is an X-linked, meaning that one of the sex cells carries the allele, then we would favor in the disorder one of the genders more than another. If you look here, I can see there's just about as many squares as there are circles. Okay, so this isn't leaning against an X-linked. This is leaning to an autosomal dominant. Let's see if I could explain that. Well, to be autosomal dominant, you need to have just one dominant allele to have the disorder. So let's put that in. I have A little a and A little a. And you say, well, could they be homozygous dominant? They certainly could be. Okay, but here is the reasoning where I think it is this. Okay, and the reasoning is they must be heterozygotes because some of the children do not have the disorder. Now, if you don't understand that, draw a Punnett square. Let's go with big A and little a, or let's go with a scenario where we have homozygous dominant and we have a heterozygote. Yes, we're going to get, you just need one dominant allele to have the disorder. So clearly everyone's going to have the disorder. If you have a homozygous dominant individual, there's at least one big A in my Punnett square, so everybody would have the disease. So there has to be homozygous recessive. Okay, or I should say, I'm sorry, should be heterozygotes. Okay, we wouldn't just call these carriers, by the way, because there's nothing to carry. If you have the unfortunate allele or dominant gene, then you have this. So what do we have here? So if we have a heterozygotes being crossed, and again, some people see this right away, some don't. Here are your possibilities. But the key thing here is that the only people who are not inflicted, guess what, are your what? Homozygous recessive individuals. So the offspring here has to be homozygous recessive. All right. Could one of the shaded ones be? Sure, but let's see what happens. Okay, we're always going to look at the children to figure out upstream. So the darkened individual here next to the second generation, that could be either a homozygous recessive or a homozygous or a heterozygote. Now, if it was, let's write it in there. Let's just say it was big A. Well, doesn't that mean every child would be inflicted? Because you're going to at least get, remember, one from each parent. So you are, if this parent right here next to 2 has 2 big A's, you are essentially going to 100% get a big A here. And that's not the case. So we can say that this is going to be a heterozygote for that reason. See what I did there? I'm using my logic. Okay. This person must be what? Homozygous recessive. It does not have the what? The disorder. And I can keep doing this now. Everybody who does not have the disease doesn't have one dominant allele. That means has to be a homozygous recessive individual. Of course, in this scenario, we have that here. Okay. Moving on, this individual, now you say, okay, could this be a homozygous dominant? If that was the case, every single offspring would have at least one. And of course, that is not the case. Okay. So we know this is a heterozygote again. Could there be a scenario written that way? Absolutely. So this would be big A, and big A, little a. All right. Now the question is, what is this female, this daughter of the first generation? What is she? Well, that individual could be either big A, little a, or big A, big A. We don't have any what? We don't have any children downstream to see what she is. So that person could be both. Okay? So that's how I thought about that. Now, going over this, what's the inheritance pattern? And I'm going to say autosomal. Again, it's not sex-linked. There isn't more females or males being inflicted. Recessive. I'm sorry, autosomal dominant. Okay, thank you for those screaming at me. Dominant, Mr. Grodsky. Okay, so dominant. Provide at least one piece of evidence for your claim. Well, I'm going to say it cannot be autosomal recessive because all of the children in the second generation would have the disease if it was, and there is no preference to gender, so it must be autosomal dominant. So basically, I'm explaining autosomal dominant by telling it what it can't be. All right? And I can also explain its pattern because if you look at the first generation, being a heterozygote means having one. All the children, okay, if it wasn't, would be inflicted. But again, the best way to explain this one is to explain why it's not the others, okay, to be honest with you. But the individuals here in my Punnett squares do work out, okay? So in any case, perfectly fine to explain why it is not autosomal recessive or one of the sex-linked inheritance patterns. But you can see clearly that the patterns do support what we did here. Now, the last question is, consider the children labeled 1, 2, and 3. That's down here. Okay. Would you expect these to have individuals to have children of their own with this syndrome? Well, if you look very carefully, the parents do not, neither of these parents have a dominant allele. So all of these individuals or the offspring, okay, if you need to do the Punnett squared for those two, would be homozygous recessive, and therefore they wouldn't show any of the disease. So, of course, that would be no, and none of the children would be expected to have the disease because both parents do not have at least one dominant allele to give them. Okay, and again, you could probably use this as another way to explain your what evidence that this is a dominant, autosomal dominant inheritance pattern. Okay, easy for me to say. Moving on to the next one. So taking a look at this second to last one here, something that jumps out at me is that we're skipping a generation for sure. So I tend to think, oh, this might be, might be, okay, autosomal recessive. It's the end of my day here, guys. I've been talking all day. All right. Any case, so I see in generation 1, 2, 3, and 4, first generation doesn't have it. So, we've seen this before. This could be autosomal recessive. Okay, clearly that's one way to go. But what jumps at me is that there are a lot more males. Okay, look at the squares. A lot more males that have the disorder than females. Females still can have an X-linked, okay, genetic disorder, but they're more rare because they have to have both alleles since they are an XX. Okay, so this, to me, although it could be, but the fact that I'm seeing all these males is making me think X-linked. So I'm going to jump there. Okay, I'm going to put, here's my male, X and Y. The nice thing about understanding the X-linked is because if the gene is being mutated on the X chromosome, a male only has to have the one recessive X, okay, to show the disease. That's why they, come up more often. They don't have a second X that's dominant to balance that lack of protein being corrected. This, of course, is XX. Now, we're seeing a male who's inflicted, we think. And so if my pattern is correct, this would be an XY. And what I'm going to draw here is a little kind of squiggly here on the Y. Oh, maybe I'll do this in red here. Okay. I don't know if that pops enough, but maybe I'll just do it in blue. Okay. So I'm just going to put that in blue there. Okay, so that means that X is a mutant or is mutated. It's the recessive. Now, how did that male? We know that the gender of offspring come from the male. So the Y, of course, came from the father. The X, so one of the X's from the female must be mutated. So there I go. There I go again. Okay, so we have another male who's not inflicted, so that just must be an XY. That makes sense. The Y came down, and the other X from the mom, okay, was given there. So that kind of makes sense. All right, and we don't know about what this person here is yet, so we'll leave that blank. Okay, and if I look at the other side of the family, or that's going to be connected here, we see the same thing over here. We see an X, and again, I'm going to go backwards to go forward to see if this makes sense. XY, and again, my X is mutated, and then we have a what? A male here that's X and Y. It doesn't have the disease. It's not shaded in, so the X can't be, okay, mutated. But like just as we said here, this parent must have the what? At least one of this mom has to have at least one of the X's mutated. If it had both, it would be homozygous recessive and it would be circled in. So it does it. That's what that's telling me. Okay, so there's a female here, and this female I'm not sure about because this female could get a what? An X that's not mutated or mutated. Okay, and I have a male here that's not showing anything, so I know for certain if this is the pattern, okay, I know for certain that this X and Y will not have it. Now, the thing is, let's go backwards. Let's go down to the 4th generation. This is an X and a Y, because I'm not sure about this, but I think I can work it out going backwards. Remember, the children downstream can help you figure out what's upstream. That's important here. So I have an XY, and it's an infliction. So, party people, I am going to put that little squiggly there to show that mutated there. And wait a minute, this is dad, and he's not inflicted, so yeah, I know he's just an XY. All right, mom is an XX. She's got to be a carrier. She's got to have one of these to make this work. Okay, and this is a female, and again, this female is XX, but I don't know which X is. One from the dad for sure, and one from the mom, so I'm not sure about this one. Okay, but working backwards, in order to have a female that produced an offspring that was a boy, it got an X that was what? A carrier. Since this male is fine, it had to come from the female, yes. Which makes sense because it got one from its mom up here. So this XX, we've got to put a little doohickey there, little thing there, and that kind of makes sense. So I kind of work backwards. And you can think why I don't know down here what this guy is, because it doesn't have any children to show me. I know it's XX, but it could be a carrier or not. Okay, females can be carriers. Okay, going over here, okay, this individual here can be a couple different things. It's a female, so it's definitely XX, but I don't know if it's a carrier or not. Okay, so what do? We look at the offspring, and I see a circled female here that I'm circling that is showing the what? Is showing the disorder. So the only way females can show it is both X's must have the recessive allele. Okay? So if that's the case, if one X came from dad, the other X came from the mom, so this mom must be a carrier. Okay? Must be a carrier. All right? And so if that's the case, we have, again, a male is here, and it's not showing the disorder, so this is going to be an XY. So again, I'm 100% certain this is an X-linked disorder or inheritance pattern. Okay, and again, what jumped out to me was definitely the idea that there was more males here. Keep going. I have a XY. Remember, your job is to fill in these boxes. And this is an inflicted male, so it's going to have a little mutated X there. And if it got its Y from its dad. The Y doesn't carry it. This X from the dad can't be having any type of inflection, or at least not mutated, because it's not shaded in. Any case, what are the possibilities for this? Well, these are girls, so this is XX. They're not showing the inflection. They can't because this X here doesn't have it, but it makes sense you're going to get one X from your dad who's not inflicted, but you're going to get one from your mom. So we definitely know that both of these have to get at least one X from their mom, and each X is mutated. So we definitely know those individuals. So that's how we worked here. And the off to the left here, I don't know what 2 could be because I don't know if they've had any children and they're not part of the family. Same, this person could be any other individual here. Well, it could be a couple of different things. Let's go back to the questions, though. Okay, so provide at least one piece of evidence for your claim that this is X-linked recessive. Yeah, so I'm saying it's X-linked, and it's recessive, which means you can have a carrier, but only for the female. All right. I said there are more males than females that have the disorder. Females must have both X chromosomes with the mutation or recessive allele to show the disorder. Females can be a carrier, but males cannot. Okay, so clearly I can definitely show this pattern as X-linked recessive. And then the last one says, the dashed line represents a possible union. Okay, possible mating, and they're going to make some kids. Discuss the probability that such a union will result in a child with CMT. All right, well, if we now know these individuals are this, I can do a little Punnett square. I can do a big Punnett square too. But so we have, let's do the female on top, X, 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 Y. And notice the X, one of the X's here is inflicted, one of these X's. And let's put these together. That's going to give me X, 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 Y, X, Y. Let's put in, this is going to be a female that has the infliction. I said colorblind, but and then of course we have this one's a carrier. This is going to be a male who's infected and a male who's not. So what we have is we have 50% of the males and 50% of the females have the disorder. Remember, females have to have both X's with the recessive allele, and the male's only one. So you would say 50% here, 2 out of 4. Very simple. On to the last one. Okay, so what's this inheritance pattern? Well, if I look at me, we're skipping a generation. So it looks like to me maybe this is autosomal recessive. But just to make sure, let's look at the individuals inflicted. I see a female, I see a male, I see a male, I see a female. I don't see a disproportionate number of males or females. So this doesn't look like an X-linked pattern to me. And looks, if we're skipping a generation, it possibly could be that we have an autosomal recessive disorder because we have parents who don't have it, which means they must be what? They must be carriers. Okay? Same thing here. This individual is homozygous recessive, doesn't have a working gene on both chromosomes to make the protein to live its function without a disease. So both of these parents must be carriers or heterozygotes. Okay, now to figure out what this individual has to be, I know it's not homozygous recessive, but it could be homozygous dominant or a heterozygote. I gotta look at the children. Look at what the children are doing. So I have little a, little a, little a, little a. Okay. And the only way to have what? No parents have disease. They, guess what? Must be carriers. You must be delivering a recessive allele to each individual. Okay. This one I do not know because I don't have any children and because it can be either homozygous dominant or a carrier. We have no more information there. We need more. But looking at this other area here, these parents don't have the disorder, but their children, or their one child does. So these must be what? These must be carriers for the same reasoning. And again, same thing here. these individuals here could be either. We need more information. So another homozygous or autosomal recessive inheritance pattern. Okay, so autosomal recessive. Again, what made it jump out to me was skipping a generation. It's not always going to work that way, but it made a lot of sense once I started putting the genotypes in. And of course, what's your one piece of evidence? Both parents that do not have the disease must have at least one recessive or mutated allele to produce the offspring. All right. Okay, so I hope that helped, and good luck.